First thing is today I updated the gradebook, so please check your grades. If there are any assignments you want to work on, let me know. There's still time. So after class, I'll be responding to any extensions. So if you want a homework extension, just send an email or use WebAssign. Okay, the next part I'll just talk about, and I'll write an email soon about how the grade is going to go. Okay, so for our class, we had 2 quizzes. We'll summarize really shorthand. Each of them will be 2%. Okay, we did 2 exams. Each of them is 15%. Okay, we're going to keep the final at 25%. Yep. But it will be mostly focused on the work we've done since exam 2. Okay, your homework was 22%. And that should be 81% total. All right, what's next? Talk about homework. I want to make homework tonight and have it due on Sunday, the 9th. And I do want to have homework from chapter 4. I don't know if I'm going to have sections, homework for sections from chapter 5. Maybe they'll, if they are, they're going to be short. So the last of the homework will be up soon. Okay, I'll list the assignments Wednesday. I need to make them still, so. They'll be short. Okay, and I think that's it. The goal for today is to get through section 5.2. The overall goal is to go through 5.2, 5.3, 5.4, 5.5. Next week is the last week of instruction. After that, we're doing finals. So we want to make sure there's time next week to review for the final. Okay. And by the way, most of everyone who's been doing homework has a pretty good grade. If you are missing assignments, though, that would improve your score. All right, let's do 5.2. On Friday, we finished 5.1, so this is the beginning of a new section. called definite integrals. Cool. We have a continuous function f on AB. Okay, closed interval that goes from A over to B. There we go, cool. And we talked about splitting up that interval into n subintervals. So we're going to say we partition that interval into subintervals. We also talked about the width of the interval. Interval is delta x. And that would be b subtract a divided by n. All right, I'm going to write down what the partition looks like. Then we'll sketch a little picture. Okay, it's a set. Starting from A, going to B, we're going to call A x naught. B is a set. Starts at A equals to x naught. X naught is less than x1, and is followed by x1, which is less than x2. Okay, so if I can make this all fit on a nice big whiteboard, it would continue straight on. But we're going to pick it up with x sub I minus 1. After that is x sub I. Okay, x sub I minus 1 is less than x sub I. After that would be x sub I plus 1, x sub I plus 2, until you get to x sub I plus n. I'm sorry, x sub n, just plain old n. That's called b. Let me close this set. Okay, we go from A over to B, and we also talked about picking values from the subintervals. So first, a subinterval would be called the ith interval. And it would go from x sub I minus 1 over to x sub I. And at this point, I feel like we should draw a picture. Okay. These are values of x. And you're going to we will integrate from a over to b. A is x naught. B is x of n. After x naught is x1 and x2 and x3. Keep going. Okay, so I don't know what n would be, but let's say here is some x of I. I should put a little bit over here. Like this. Okay, behind it is x of I minus 1. And then let's say you go straight from x of I minus 1. The next one will be over to x of I, over to x of I plus 1. And then whatever is next is x of I plus 2. And we keep going until we get to it. Okay, so an ith interval would go from like here to here, x of I minus 1 to x of I. Right, from each interval, you pick a tag. So we'll usually pick right-hand endpoints, or you could pick left-hand endpoints, or you could pick midpoints. Any point from that interval would work. We call it x of I star. And then we can put it all together into a definite integral. So the definite integral from x equals a to x equals b. Is going to look like this. The integral, it's kind of like a stretched out S integral. And you begin the integral from like the beginning of your interval, and it ends at the end of the interval. So integrate from A up to B. And we are going to integrate our function f of x. Dx means with respect to x, like integrate with respect to x. So definite integral is this right here. And it's equal to. We need space. Okay, it's the limit as n goes to infinity of the sum from I equals 1 up to n of your function, but you put in that tag f of x of I star, multiply by delta x, and then close that up, and then find the limit. Again, this symbol right here is for integration. This is where you start, this is where you end. That's your function. That's what you're integrating with respect to. And this is, everything on this side is called a Riemann sum. That has a special name. Okay, so again, we're going to have a picture. We talked about how each of these is a rectangle, and then we add infinitely many rectangles under the function, and that gives us that area. So this is the area under the function to the x-axis. I like to draw A to B, a function f. And then the integral from A to B is the area under the curve from f to the x-axis. So the integral from x equals a to x equals b of your function with respect to x is the area under f to the x-axis. From a to b, from x equal to a to x equals b. Okay, so I have a function where all we have is a graph, but we're going to be able to integrate the function by finding the area under the curve to the x-axis. Okay, so the function is called f. Put that over here. It goes from 0, 0 straight to the point 1, 2. And then over flat right above 3. Back down to 4, 0. And then a half circle between 4 and 6. Height 1. So that's supposed to match up with 1, and that's like y equals 2. The definite integral, we're going to go from x equals 0 over to x equals 6. Actually, let's make that nice and clear. x equals 0, x equals 6, our function f, whatever it is, f of x dx. So we're trying to get the area under the curve from f to the x-axis. Right here, we're going to get the area of that rectangle. This would be a square that's 2 by 1, and then cut it in half. So an area of 2, and half of that is 1. Okay, then we've got this square shape. An area of 2 by 2, so it's area 4. Okay. Here's another triangle with area 1. And this circle has a radius of 1. So the area is pi times the radius squared. The full circle would have pi times 1, and then we cut it in half, so it's 1/2 pi. So 1 plus 4 plus 1 plus pi over 2. 6 plus pi over 2. All right, so that worked out nicely since our function was positive, it was above the x-axis. But area is going to be the net, a definite integral is going to be the net area. So we're going to draw, I'm going to draw kind of an abstract picture, and I'll make up an actual function. Okay, so let's say you have your function go. Let's draw a picture first. We're going to go something like this. That's our function. Okay, we're going to take this area here, and then we're going to subtract the area that's below the x-axis. So subtract whatever this area is. But then this area that's above the x-axis, we're going to add to the overall area. So add, subtract, add, and that's going to be the integral for f of x. Something like this, the integral from a to b of f of x dx is the net area trapped between f of x and the x-axis. I guess between f. I think it's better to say f than f of x. I like to say f of x, but the function's name is just f. And that function to the x-axis. Cool. So our next example. Draw some function f. Cool. We want our function to go from 0 to and then connect to 2, 0. We're going to have a half circle with radius 1, so we're going to go down to -1. It's a pretty good half circle. Okay. And then from 0, 4 up to 6, 2, it's a straight line. Cool. We are going to get the integral from x equals 0 over to, let's start with over to 3, to x equals 3, for that function f. Okay, so this would be part A. The integral from x equals 0 to x equals 3 looks like this. Of your function f. It's a function of x and dx. Actually, I want to go from here to here. So we're going to get this area and subtract the area that goes halfway through that circle. I guess it's a fourth. It's a fourth of the circle. Okay, this piece. The square would be 2 by 2. So the area of the square is 4, and you want half of that. So the area is 2. Oh, I also have that. Nope, never mind. I need to mentally block off everything past 3. Okay. That piece and just that piece. 2 minus. See, half of a circle would be pi over 2, so half of that half is going to be pi over 4. Next one, we integrate from x equals 2 to x equals 6, and it's going to be for the same function. We don't have any. All right, so before I erase and set up part B, I just want to remember that we're going to go from 2 over to 6. So this is the integral from x equals 2 up to x equals 6 for your function f of x, and then the dx means integrate with respect to x. Cool. We need to go and get the area that's this way. We have a negative area of pi over 2 and a positive area of 2. So negative pi over 2 plus 2. All right, so this time we wanted to take this piece of area and that piece of area. Okay. I have a third example and then some rules. Just want to make sure I don't lose track of time. Number 3. We're going to approximate the following integral. It's the integral from 1 to 5. The function is x squared times e to the negative x. And then dx. We're going to use, let's see, right-hand endpoints with n equal to 2. I think I want to draw the interval and then break it into those 2 subintervals, and then we'll create the rectangles and probably draw a picture. Actually, I have no clue what that function looks like, so we're not going to draw a picture, but we will just get this set up here. So first, we're going from 1 to 5. Okay, let's find delta x. Okay, 5 minus 1 divided by 2. So 4 over 2 is going to be 2. So the width of each subinterval is width 2. So 1, 2, 3. 3 to 4 to 5. And we go from here to here, create a rectangle, here to here, create a rectangle, and use your right-hand endpoint. So from the first interval, or subinterval, the right-hand endpoint is 3. And your next subinterval, the right-hand endpoint would be 5. Okay. I think it's good to just rewrite the problem and then put together the approximation. So we're looking for an integral from 1 to 5. X squared e to the negative x dx. And it will be about what we call r sub 2. We used right-hand endpoints with n equal to 2. That is equal to delta x times f of 3. Delta x is 2. 2 times f of 3. Add delta x times f of 5. And then I just put those into your function. This is your function right here. Okay, so this is 2 times 3, putting in 3 here. 3 squared e to the negative 3. 2 times f of 3, and that gives us a 3 squared. A negative 3. And then add 2 times f of 5. Put in a 5 squared, e to negative 5. Cool. Almost done. We have 18 over e cubed plus 50 over e to the 5th. And I just left it like that. Okay, so in 10 minutes, I'm sure we can cover the rules for sums, and then we might have to save the examples for next time. Let's do it. First one, the sum from I equals 1 up to n of some constant c, so some number c, is n times c. So repeated addition becomes multiplication. Number 2. Okay, there's a bug on my computer. We're just going to ignore it. Okay, the sum. From I equals 1 to n of c times a sub I. So whatever, what did I say? You have some kind of expression that is being affected by that subscript. So it needs to stay in the summation sign, but the constant can come out. So you can have your constant and then multiply with the sum from I equals 1 to n of your a sub I. Number 3. We have a sum from I equals 1 to n of a sub I plus or minus b sub I. Okay, you have the sum of your a sub I and then plus or minus sum of b sub I. So sum from I equals 1 to n of your a sub I, and then plus or minus sum from I equals 1 to n, b sub I. The fourth one is the sum from I equals 1 to n of I. So your sum I equal to 1 up to n, and you're summing I. You get n times n plus 1 divided by 2. And we're going to do the sum for I squared and the sum for I cubed. the sum from I equal to 1 up to n of I squared. Okay, is n times n plus 1 times 2n plus 1 over 6. Okay, last one is number 6. We're going to sum from I equal to 1 up to n, I cubed. And I have to check this out. Okay, so I have it written as n times n plus 1 over 2 and everything squared. So we still have 6 minutes, which means I think we can do at least one example. We'll save the other one for next time. We're going to try to find the integral from 0 to 3 of 25 minus x squared dx. And that's it for today. Okay, integral from 0 to 3 of 25 minus x squared. Going to do that limit. So I'm going to write down what it is in general, and then we'll actually do all of the work to find the limit. Okay, so we want the limit as n goes to infinity. The sum from I equals 1 up to n. Let's start out with the f of x of I star. Okay. Delta x. Okay, I will do right-hand endpoints. Let's just summarize that with r sub n. R sub n, right-hand endpoints. And let's look at what that would be. So we're iterating from 0 to 3. And, oh, I can find delta x. We'll put that, we'll put that soon. But if we're going to go, no, I need delta x. Okay, I can't picture this without knowing that. So we need 3 subtract 0 divided by n. 3 over n. Okay, so from 0, we add 3 over n and 3 over n and 3 over n. So let's talk about the very first subinterval from 0 to 3 over n. The right-hand endpoint is 3 over n. And then the next right-hand endpoint is adding another 3 over n. So we have 6 over n. So we want to put in 3i over n. let's just write about it. Okay, so equals the limit as n goes to infinity of the sum from I equals 1 up to n. Okay, in your function f, we're putting in right-hand endpoints, which will look like 3I over n. And we multiply that by delta x, which is 3 over n. Okay, so let's do this part. Just putting in your 3I over n into that function f, this piece here. Okay, so we're here. I'm going to continue the limit. As n goes to infinity of the sum. The sum from I equals 1 up to n. We're out of time. Okay. I'll just mark that down where we got to. I'm going to put this into our function, and then we'll come back next time. So we've got a 25 minus 3I over n squared. That's my function f with this guy inside, and then multiplied by delta x, which is 3 over n. And then after that, we're going to find the limit of everything, but that'll be next class. Okay. Okay, so I'm making the last of the homework tonight.